Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Sabrina and my metric number is 2316850. I will be presenting on the fascinating topic about azeotropes. First, let's begin with the definition of azeotropes. Azeotropes are a constant boiling point mixture of two or more liquids that maintain its composition and boiling point during a distillation. This means that all the components of this solution boils at the same temperature with the same composition of components in liquid phase as well as the vapor phase. The proportion of components cannot be altered by simple distillation. This is because during a simple distillation, the mixture is heated and the vapor is condensed and collected. However, due to the vapor has the same composition as the liquid, the collected liquid will have the same composition as the original mixture. Consequently, it is not possible to separate the components of an azeotropic mixture by simple distillation only. Thus, to separate an azeotrope mixture, additional techniques are required such as azeotropic distillation or extractive distillation.
My name is Nur Afifah binti Muhammad Fauzi, metric number 2316468.
Azeotropic distillation. Azeotropic distillation is a specialized process to separate components in azeotropic mixture. Originally, due to its nature, azeotropic is hard to separate by using simple distillation. Hence, an azeotrope breaking agent known as entrainer is added. Entrainer alters vapor-liquid equilibrium, volatility of the system, by disrupting the azeotropic behavior. Here's how the process goes. First, the mixture along with entrainer is heated in distillation apparatus. Then, entrainer forms new azeotrope with one of the components. During vapor phase, which now contains entrainer, is separated from liquid phase in distillation column. Later, entrainer can be separated from the desired component using further distillation or other separation technique. This process is commonly used in chemical and pharmaceutical industries to separate mixtures of liquid that are difficult to separate using simple distillation. Azeotrope distillation is an important tool for producing high purity chemicals and pharmaceuticals.
My name is Nur Shafiza binti Khafi, number matrix 2311454. Today, me and my friend will be explaining the types of azeotropes. When we mix chloroform and water, they form two layers, the top layer consisting mainly of water and a small amount of chloroform. The boiling point of this mixture is observed to be lower than that of the boiling point of either water or chloroform. This is what we call heterogeneous azeotrope, where the constitutions of a mixture are not completely miscible. Another kind of azeotrope is a homogeneous azeotrope, where the constitutions of a mixture are miscible completely. For example, if we boil a mixture of 60% ethanol with water, we will get a vapor of 60% ethanol with water. This azeotrope will also be homogeneous as alcohols and water are miscible.
My name is Fatin Akila binti Ibrahim with metric number 2318212. For third type is negative azeotrope. Actually, negative azeotrope is similar to positive azeotrope, as the vapor and liquid phases is maintained a constant composition during the heat process. The highlight is negative azeotrope occur when the mixture solution is boiled at higher temperature compared to the boiling point of poor substance. As you can see, the graph of the temperature is down outside, which is opposite to the U-shape, and the graph for pressure will be a U-shape due to the relation of temperature and pressure, which is inversely proportional. As example, the azeotrope boiling point is higher than the acid, hydrochloric and water boiling point. Lastly, binary and ternary category is referred to the mixture itself. Binary involves two components that being mixed together, such as ethanol and water or acetone and methanol. Contrast to it, ternary is referred to mixture of three substances where the behavior becomes more complex. Before I pass to my friends for the next topic, let's look at one example for this topic. Based on this question, it asks us about the graph. As the temperature of azeotrope is lower than the poor substance ethanol, we can make a graph to visualize it. Based on the graph that we draw, It is a U-shaped graph which is a positive azeotrope. That's all from me.
Hi, I'm Imanul Asma binti Muhammad Sabri with metric number of 2314826. And we are moving on to the next topic, that is non-ideal solution. Firstly, we want to know what is non-ideal solution. Non-ideal solution is a solution that does not abide to the rules of an ideal solution where the interactions between the molecules are identical or very close to the interactions between molecules of different components. In another word, non-ideal solution cannot be defined by Roots law, meaning the vapor pressure of the solution does not equal to the mole fraction of solvent times the vapor pressure of solvent. Next, what is the difference between non-ideal solution and ideal solution? Ideal solution does obey Roots law, and the enthalpy H of mixing is equal to 0, means no heat is absorbed or released during the dissolution. And the mixing volume is equal to 0, means the total volume of the solution is equal to the sum of the pure liquid mixed to form the solution. Whereas, non-ideal solution does not obey Roots law, and the enthalpy H mixing is not equal to 0, means the heat is absorbed or released during the dissolution. Next, the mixing volume is also not equal to 0. The total volume of the solution is not equal to the sum of the pure liquid mixed to form the solution.
My name is Sufi Madiha binti Muhammad Nazri. My metric number is 2317858. Now I'm going to explain about the deviation from Roots law. As we know, an ideal solution refers to a mixture where the interaction between solute and solvent follows the ideal law, namely Roots law. However, in a non-ideal solution, it shows deviation from this law. So, those solutions which do not obey Roots law are said to be non-ideal solution. First of all, let's compare the diagrams between the ideal solution that obey Roots law and non-ideal solution that deviate from Roots law. The first graph represents the ideal mixture. It shows how the vapor pressure of two components A and B in a liquid mixture vary according to the composition of the mixture. It's a straight line relationship and the total of vapor pressure is directly proportional to the mole fraction of A and B in the mixture. This ideal behavior only happens when the interaction between the molecule of A and the molecule of B are no difference in strength from the interaction in pure liquids for very similar liquids like hexane and heptane. As shown in the poster, non-ideal solution exhibit two types of deviation from Roots law, which is positive deviation and negative deviation. In positive deviation, A-B interaction is less than AA interaction and BB interaction. A-B interaction are those interactions which we get after mixing individual components of A and B, while AA and BB interaction are the interaction that taking place within their individual components. From this, we can conclude that in solution phase, the interaction between A molecule and B molecule is weaker, and hence the particle of A and B will move away from each other, and both molecule A and B can escape more easily into the vapor phase. Besides that, the volume of the mixture is greater than 0. In positive deviation, it also shows that the delta H mixing is greater than 0. To understand this matter, we can imagine that when A-B interaction are weak, it means the stability of the liquid mixture has been lost, but they were stable individually. A molecule stable individually and B molecule also stable individually, but after mixing both of them, they have lost their stability. Due to this, they will absorb energy and lead to the delta H mixing greater than 0. From the graph, we can see that the vapor pressure of both A and B are more positive, greater than Roots law would predict, and so the total vapor pressure for this kind of mixture is said to display positive deviation of Roots law. For example, mixture of propanol and carbon disulfide.
My name is Aina Mardia binti Ahmad Salihuddin, matrix number 2319164. Now I will continue with the negative deviation. In negative deviation, it contradicts the positive deviation of Roots law. In this case, A and B interaction is more stronger compared to AA and BB interaction. That means the particle of A and B is closer to each other, and they escape less easily into the vapor phase. As a result, the vapor pressure of both A and B and the total vapor pressure are more negative than the Rhodes law would predict. This can be interpreted through the graph of negative deviation from Rhodes law that is present in the poster. It also indicates that the volume is decreasing, or we can say that delta V mixing is less than 0. Additionally, in the negative deviation from Rhodes law, when the interaction between A and B is stronger compared to the interaction between AA molecules and BB molecules, this means energy is released. Or we can also say that this is an exothermic process. This results in a decrease in the enthalpy of mixings. Hence, the delta H of mixings is also less than 0. Mixtures of propane and trichloromethane show this kind of behavior. Now we will move on to the problems related to non-ideal solution.
Based on the first problem, we identify that acetone and chloroform will form a non-ideal solution because hydrogen bonding between the two molecules will produce forces of attraction between unlike molecules, which is acetone and chloroform, that exceed those between like molecules, acetone and chloroform. The second question is a calculation based question. So the first thing that we need to do is list out all the information given, and then we can just plug in the value into our formula, and we will get vapor pressure of X is 21.33 torr, while vapor pressure for Y is 50.67. Then we sum up both value, we will get P total, which is total vapor pressure is 72 torr. Then we can see that observed vapor pressure, which is 70, that given from the question, is less than the expected value, which is 72. Thus, the solution shows that it does not obey the Rhodes law and it shows negative deviation.